All right, everyone, welcome to the next part of this video where I'm just going to dive in and solve some of these problems. But I just realized in the last one I did not discuss concavity, so let's do that real quick. When I have a concave up function, or part of a function, that means that the rate of change is increasing. All right, up, increasing. And let's just explain that for a second, right? Here I have a pretty steep negative, so let's just call that -3 for a second. Maybe that's -2, maybe that's -1. Well, here is 0, then 1, then 2, then 3. So the rate of change is going up over a concave up function. And it's the opposite for concave down. This concave down looks like a frown, easy to remember. Right? Well, here I have something like, maybe it's a pretty steep slope, 3, and then it's getting decreasing, and then it's decreasing, maybe it's 1. At any vertex or local min or local max, it's 0, where we change direction, -1, -2, getting steeper, -3. So it's going down, so the rate of change is decreasing here. Okay, so that should let us answer some of these questions ahead. Find the intervals of the function graph below where the rate of change is increasing. Well, I'm looking for where it's concave up. Looks like it's concave up from like here. Concave up, concave up, concave up. Then looks like about here I have a point of inflection. A point of inflection is where the concavity changes. So it looks like it goes to concave down there. So I'm looking for an answer choice that's, well, maybe they're assuming that this was concave up the whole time. So this might be from -infinity to about 1. Let's see if there's an answer choice that's exactly that or close to that. Oh, not 1, -1, right? That's why attention to detail matters in math. Okay, so there, I see it. -infinity to -1. Okay, find the intervals of the function graph below where the rate of change is decreasing. Well, decreasing means that it's concave down. Looks like here, this is clearly concave up, right? Concave up, concave up, concave up. And I don't know, somewhere around here, maybe at 5, we hit a point of inflection. And it looks like we turn to concave down, concave down, concave down, concave down, and we stay concave down forever. Down looks like a frown, so I'm looking for some interval that seems like 5 to infinity, and there it is. All right, find the intervals of the function graph below where the rate of change is increasing and decreasing. What do they mean by that? Well, okay, we got some answer choices here. The function rate of change is decreasing from -infinity to 2 and increasing from 2 to 5. Before I look at these answer choices, let's just look at the graph. So we can say at the beginning here, I am clearly concave down, concave down, concave down, concave down. And then here, at 3, I look to hit some point of inflection. So it looks like we are decreasing from -infinity to 3. Then we switch to concave up, concave up, concave up. Looks like that goes on forever. So from 3 to infinity, we are increasing. So let's find an answer choice that resembles that. Well, certainly this is involving 2. So this is 2 is not a point of inflection, right? That is just where it changes direction. All right, the function's rate of change is decreasing from -infinity to 3. I agree with that. And increasing from 2 to 5. I don't agree with that at all. From 2 to 5, that's, let me grab a different color. That's here to here. Well, first of all, it's just not right. All right, we can move on. From -infinity to 3, 3 to infinity. Oh, there we go. We've got the right answer. All right, Again, increasing and decreasing. We have different notation this time. We're using inequality notation. I really prefer interval notation, but the answer choices are the answer choices. All right, let's see. Look, we start concave up, concave up, concave up, concave up, concave up. I think it switches here at about -4. So from negative infinity to -4, we're increasing. Increasing rate of change, I should be clear. Increasing rate of change, which is different than the function increasing. And from here, we're concave down, concave down, concave down. Looks like we're concave down forever. From -4 to positive infinity, the rate of change is decreasing. All right, so the function's rate of change is decreasing from -4 to infinity. I agree with that. And increasing from negative infinity to -4. This looks pretty good. So I don't know if I need to look at the other answers. This has a 6 in it. That's not right. This has a 6 in it. That's not right. This has a 6 in it. That's not right. All right. Those are pretty easy questions. You will most likely see some of these on your exam, and you need to get them right. All right, a couple more increasing, decreasing ones, because we need to be able to differentiate between a rate of change increasing and a function increasing or decreasing. So we've got this function here with some labels on it. It says the graph of h of t and its dashed midline for 2 full cycles is shown. 5 points, f, g, j, k, and p are labeled on the graph. No scale is indicated. No axes are present. The t-coordinate of g is t1, and the t-coordinate of j is t2. On what interval is t1 to t2? Which of the following is true about h? So we're going from g to j. That's a lot of stuff just to tell us about g and j. Well, we're asked about h. That's asking about the function, not the rate of change of the function. That is different. A function is positive or negative. Well, it's positive when it's above the x-axis, so when it's up here. A function is negative, let's just switch over to blue or red, when it's below the x-axis. So let's check to see if our function is positive or negative. Well, I'm just going to look at the y values here. All right, I don't want to be deceived by this. This is not an x-axis. The y values are positive. So that means we're above the x-axis. So this function is positive. This function is positive. That doesn't mean the rate of change is positive. All right, so I know it's not C. I know it's not D because this function is positive. Well, is it increasing or decreasing? Again, it's asking about the function, not the rate of change. I know it's confusing. I know it's kind of annoying that we don't have better ways to discuss this. Well, is the function, not the rate of change, going up or down? Well, from here to here, it's going down, so it's decreasing. So we have a positive it's positive and decreasing. That's the function, not the rate of change. Being able to differentiate between what the function is doing and what the rate of change is doing is absolutely core to calculus. So describe how the rate of change is changing on the interval t1 to t2. Well, what is happening to the rate of change? Well, this is concave up. It's concave up. So the rate of change is what? Increasing. The rate of change is increasing. And just to dive in a little bit more, so here it's concave up over this, so it's increasing. Now, another way we might say, let me just say this is not in the question, j to k, it's still concave up. Here it's increasing, the function is increasing, right, at an increasing rate. That's another way we can see this. But over here, the function's going down, so it's decreasing the function still it's concave up, increasing rate. All right. So I know it's some weird vocabulary in this section. I know my handwriting's bad, but just take some time to grapple with those statements. All right, let's go over one more. This time we're looking at from K to P. Switch colors back to something you can see. K to P. And okay, well, first I want to discuss if the function is positive or negative. Well, my y values are, well, mostly negative until 0. So that means this is a negative function because we're below the x-axis. So bam, bam, it's a negative function. Well, are we going up or down? And now hopefully this is pretty easy. Well, we're clearly headed up, so this function is increasing. So we are negative and increasing. Now what about the rate of change, which is different than the function? Well, the rate of change, we are concave down here. We're clearly concave down. So the rate of change is decreasing. And actually, I'm not sure, maybe in this one I should have said, because we're only looking at from what to what? From G to J. I should have said, actually, I should have given this full answer here, that we're decreasing at an increasing rate. So the rate of change is, no, that's the function. Okay, actually, no, this is fine, because we're asking about the rate of change. My bad. See, even I get confused a little bit about it. So the rate of change is decreasing. All right, let's head over to part 2, where we want to sketch some polynomial functions. I'm just thinking about a second how I'm going to break this up. Yeah, this will include part 2 and part 3 as well. All right, so we have a polynomial function given as x to the 5th times x plus 2 squared times x minus 4. And first question it asks us is, what is the degree of the polynomial? Well, I had to look at this real quick. What form is this in? Well, this is clearly in factored form because these are all multiplying by each other. This is factored form, so I'm going to add up these degrees. Here's a 5 and a 2. 5 plus 2 is 7. And that's wrong. I cannot forget about this 1 here. The degree of this polynomial is 8. So the degree is 8. All right, well, 8 is an even number, so this function is even. Wrong again. The end behavior of this function is even. So I do know that while we have a positive leading coefficient, I do know that the end behavior is going to look something like this. The definition of a even function is that all of the terms are even. That is not going to be true when I convert this to factored form. I know that for a fact because these are not all even. Even if they were, that wouldn't guarantee that's even. But the fact that they're not, this is going to be neither. All right, sketch a representation of the graph. Label all the zeros and local min and max. All right, so let's start by finding the zeros of this function. I'm going to set each factor equal to 0. I get x equals 0, x equals negative 2, x equals 4. So let's plot those on the graph. Negative 2, 0, and 4. All right. So, well, we already said the end behavior is even. So and with a positive leading coefficient, so it should look something like this. So I'm going to start by coming down, because I know my end behavior starts like this. I'm going to come down at this negative 2. Am I going to go through it or bounce off of it? Well, where's negative 2? Negative 2 has an even degree. The factor does. So I'm going to bounce right off of that guy. If it's even, you bounce off. If it's odd, you go through. 0, well, the degree there for that factor is 5. So I'm going to go right through that. And then 4, that's a degree of 1. I'm also going to go right through that. And then I head off forever. Does my end behavior resemble what I sketched up here? Yes, it does. Quadratic end behavior, quadratic end behavior. We've already labeled our zeros. Let's label our local min and max. I have a local min here and a local max here. All right, any other questions on this? Yes, describe the end behavior of the graph using limit notation. Okay, well, what happens as x heads towards negative infinity? Where does this graph head? As I go forever in this direction, where are we headed in the output? Well, it's clearly headed up. So that means as the limit approaches negative infinity, the f of x is equal to positive infinity. And I'm headed towards positive infinity in this direction as well. So I can say as the limit of x approaches positive infinity, the f of x is also equal to positive infinity. Oh man, a lot of questions on this. All right, on what intervals is the f of x greater than 0? Well, clearly from here to here. So that's negative infinity to negative 2. I'm not going to include, I'm going to use double parentheses here because this is just greater than. It's not greater than or equal to. Where else are we? From negative 4 to, or sorry, positive 4 to infinity. So we're also going to include positive 4 to infinity. All right, let's hop over to this one. What is the degree of this function, g of x? Well, I have, I'm in standard form, right? Because these are separated by plus and minus signs. So that's easy. I just pick the highest exponent, which is 5. The degree here is 5. Is this function even, odd, or neither? Well, all the terms are odd. So this function is odd. We'll talk a little bit more about even and odd functions in a second. All right, sketch a representation of the graph. Label all the zeros, local min and local max. Well, if I'm going to find the zeros, I need to convert to factored form. So I need to factor out the least common multiple. And this is going to be an interesting question. I'm going to factor out negative 3x to the third, because there's an x to the third in here, there's an x to the third in here. And I'm left with x to the x squared plus 25. Now this is really interesting because, I'll be honest, I meant to make this a negative 25. That's not a negative 25. There is, so really if I wanted to rewrite this, let me just so you can see it. X squared plus 0x plus 25, right? There's that 0x term there. So I'm really asking myself, what two numbers multiply to positive 25 and add to 0? There are no such numbers. So this is the most that I can factor it right here. So what does that mean? Take a second and make a hypothesis. Does that mean there are no zeros? Does it mean that there is 1 0? Let's graph it so that you can see it. So we have the g of x is equal to negative 3x to the 5th and minus 75x to the 3rd. We have 1 0, and that should be exactly what you hypothesized, because just because this doesn't factor doesn't mean I can't set this equal to 0. And so I can say negative 3x cubed equals 0. Divide by negative 3. Anything divided by 3, or 0 divided by anything is 0. So I get x cubed equals 0. I'll take the cubed root of each side. X is equal to 0. So I do have a 0 at 0. That's my only 0. So we have a 0 here. Well, we know that this end behavior, the end behavior here is going to look linear because it's to the 5th, and this is a negative leading coefficient, so the end behavior should look something like this. Let me double down on that in a different color. End behavior should be a negative linear function. So I'm going to come down at this, and I hit 0. Am I going to bounce off it or go through it? Well, this is to the third power, so I'm going to go right through. And we're going to look something like this. All right. This should not look like a vertical asymptote. So just one more time. There we go. All right. So we don't have any local min or local max. It's just absolute, or neither of those either. So, okay. We have a graph of our function. I guess I should label this as 0. Discuss the end behavior. Well, what's happening here? As the limit, as x heads towards negative infinity, where are we heading here? We're heading towards positive infinity. So the g of x is equal to positive infinity. What about as we head towards positive infinity on the x? Well, where are we headed? We're headed down forever and ever and ever. So we're headed towards negative infinity. All right. So on what intervals is the g of x greater than or equal to 0? Or sorry, less than or equal to 0. So that starts right here at 0, and we head down this way forever. So where does it start? It starts at 0, and I'm going to use a bracket this time because of this guy saying include it, and all the way to positive infinity. I'll still use a parentheses for positive infinity because we can never reach infinity. All right. There's a bunch of these. This is just a really important skill. If this feels tiresome and easy, that's good. We want it to start to get a little boring. It's so easy. All right. What is the degree of this function? Again, I'm in factored form. Kind of just zero in on this. That's x squared. 2. We know at this point that when a function has a degree of 2, that it is quadratic. Not just the end behavior this time. It's actually a quadratic function. Is the function even, odd, or neither? Well, I have both even terms and odd terms. So we're going to say this is neither even or odd. Let's sketch a representation of this. Label the zeros. Well, we're going to need to factor this. This is a pretty easy one to factor. We have no leading coefficient, nothing to factor out. So I'm asking myself what multiplies to negative 60 as a negative 4. That should be x minus 10 and x plus 6. I set those factors equal to 0. I get x equals 10 and x equals negative 6. Those are my zeros. What is it? Negative 6, positive 10. This opens up. I'm just gonna whoomp, whoomp. Perfect. I have a min right here. We could even find this exact point, right? You know how to find the vertex using algebra 1. But we don't need to do that here. All right, describe the end behavior. Well, what happens here? All right, well, as the limit as x approaches negative infinity, where's this headed? Well, it's concave up, so it's going to head towards positive infinity, and it's the same for when x approaches positive infinity. Now, if the end behavior is quadratic, these should always be the same. The end behavior is linear, then these would always be opposites. All right, over what intervals is h increasing at an increasing rate? So, where is h increasing? That means where is h going up? Well, it starts right here. Well, we do need algebra 1 for this. All right, well, you don't actually need algebra 1 for this. The vertex of a quadratic is always halfway in between the zeros. So what number is halfway in between negative 6 and 10? That's 2. So this vertex is going to happen right here at 2. So this is a great question. From 2, where is it increasing at an increasing rate? So it's always concave up, so it's always at an increasing rate. This is a great question. Take some time to really think about this. All right, so this is going to be from 2 to positive infinity. Maybe we won't see that on a pre-calculus test, but we just love math, so we love a good question. All right, last one. We've got x plus 5 squared times x minus 11 squared. We're in factored form. I got a 2 here and a 2 here. I'm going to add those together. My degree is 4. Is this function even or odd? I'd really had to expand this to get a good idea, but if I did expand it, I can already tell that this would be... I don't really know how to teach you guys just to be able to eyeball it like this, but I know if I expand this out, I guess binomial theorem, which we'll have to go back to at some point, I know if I expand this out, like all these x's are going to multiply to x to the 4th. Would this be even? No, because the 0... all right, one way to just think about it, why would this not be even? All right, let's give a better explanation. I'm going to draw it, and then I'll show you why it wouldn't be even. Even function looks the same on both sides of the axes. So like if I have a quadratic function like this, it doesn't look the same on both sides. If I have one that's perfectly symmetrical over the x-axis, that would be even. This one, well, if we find our zeros, I think it becomes pretty... Our zeros are at -5 and positive 11. Those are our zeros. And I think if you sketch this real quick, right here, if I'm at -5 and positive 11, it cannot possibly be the same on both sides. The zeros would have to be inverses of each other. So if this was -5 and 5, yeah, it could be even. But these zeros are different, so this is going to be neither. All right, sketch a representation of the graph. Let's do that. Okay, so label the zeros. All right, well, we already have the zeros as -5 and 11. This is an even function with a positive leading coefficient, so we're going to open up like this. So I'm going to start coming down at this -5. I'm going to bounce off of it because of this 2 right here. And then I'm going to also bounce off of this 11 because of this 2 right here. And we've got a max, a min, and a min. Now, it's not the same on both sides. It's not reflecting, just to go back to the even odd thing, if I couldn't fold this over top of each other and they would be the same. So that's why it's neither even or odd. Discuss the end behavior. Oh my goodness, this is just tiring at this point. Obviously, as we head towards negative infinity, what is the j of x is positive infinity because it's open to up quadratic. And it should be the same over here, even end behavior. Alrighty, over what intervals is j of x greater than 0? Well, real quickly, that's from here to here. So from negative infinity to -5, I'm using a parentheses because there's no great equal to sign. And from 11 to positive infinity, again, parentheses because no equal sign. And we're done with part 2. Hopefully you're pretty good at these questions by now because they have so many elements of polynomials that if you can do these, you can really do most polynomial questions. All right, even and odd functions. How to show it algebraically. I think this is kind of unnecessary, but the curriculum seems to be pretty into this. We know all the terms have to be odd for it to be odd, right? All terms have to be odd for it to be odd. And all terms have to be even for it to be even if that's, if I have a mixture I have a mixture of even and odd terms, let's say 2x squared plus x, then it's neither. I mean, it's really easy just to eyeball it. But the curriculum seems pretty set on how to show it algebraically, and I'm pretty sure it's going to come up on the test. So let's just read this. I provided some of the instructions for you to refer back to since we didn't cover this a lot. Substitute negative x in for x everywhere in the function and analyze the results of the f of negative x by comparing it to the original function, f of x. So an even function, f of negative x and the f of x should be equal to each other. So if the f of 2 is equal to 4, then the f of negative 2 should also be equal to 4. All right, that's an even function. Now, for an odd function, the f of negative x, so let's say f of negative 2 equals 4, should be equal to the negative f of x. What does that mean? Well, think about it on a graph. A linear function is odd. So if the f of negative 2 is 4, then the f of 2 should be negative 4. So the f of 2 should be negative 4. So even is going to have the same output. Odd is going to have the opposite output. And you can see some of these proofs here. Okay. Look, we have x squared plus 4. They substitute negative x in for x. Well, negative x to the second power is the same as x to the second power. It's the same function. Odd function. Well, look. Substitute in negative x. Substitute in negative x. We get negative x cubed plus 2x. Factor out the negative. We get negative x cubed minus 2x. So it's this negative factors out. It's the opposite. Okay? Neither happens then. Look, I mean, these rules work fine that I showed you and are actually quite easier, right? Even, constants don't matter. Both are odd, so it's an odd function. I got an even, I got an odd, so it must be neither. But let's work on showing these algebraically real quick. All right, so I already know, just by looking at it, I know it's even, right? This constant's irrelevant. There's only a negative x squared, but let's just prove it. The f of negative x equals negative x squared plus 10. Well, negative x squared is the same as x squared, so I get the negative f of negative x equals negative x squared plus 10. Oh, look, we're back where we started. And just to finish this proof, the f of x equals the f of negative x, which means that it is, yes, even. All right, again, just looking at this one, this is an odd term, this is an odd term. I know that it's odd. All right, I'm going to substitute in a negative x. So I get g of x equals 2 times negative x cubed plus 5 times negative x. I'll simplify this. We get negative 2x cubed minus 5x. Well, I can factor out the negative. Negative times 2x cubed plus 5x. This is the same, right? This is the f of x, or g of x. Here's that negative. So here's proof that the g of x is equal to the negative the g of negative x is equal to the negative g of x. I don't really know how to read that properly. All right. So just when it's the same function but that negative is hanging out on the end, it's hard to just read this and differentiate between, obviously, negative g of x, g of negative x. Oh yeah, that's how we read it. All right, the g of negative x is equal to the negative g of x. Okay. Here, I know this is neither. I know this is neither. Just looking at it. Here's an even term, here's an odd term, here's an even term. Okay, but to prove it, I'm just going to say the h of negative x equals negative x to the fourth plus negative x to the third plus negative x squared. Well, the h of negative x equals x to the fourth minus x to the third plus x squared. This is not the same as this because of this negative right here. So this is not even. Even? No. All right, well, the odd check would be to factor out a negative. So let's set factor out a negative. You get negative x to the fourth plus x to the third minus x squared. Is this the same? No, it's not. So it's now not odd either. Alrighty. I kind of just recommend transforming this to standard form first. So let's do that real quick. We get x squared. I'm going to take a little bit of a shortcut here. That's what this simplifies to. Now its standard form is a little easier. So I can say the j of negative x is equal to, we're substituting it into negative x. And we know this is neither, right? Because we have even, odd. We know. But let's do it anyways. J of negative x equals x squared minus 2x minus 15. This is not the same, so it's not even. And if I factor out a negative, it is once again not the same here, so it's not odd. All right, I think that's everything for polynomials. So we're going to end this video and pick up on the next one